cosa devi fare? Stai condividendo? Ok. Perfetto. Perfetto. C'è sempre l'immagine, ma va bene. Se non si può togliere niente, lasciamo.
Rita. Come fa? Penso di
No, il foglio a quadretti ce li hai? Forse è meglio con il foglio a quadretti. Successo. Sì. L'immagine non la puoi togliere, vero Rita? Questo è qui. Va. L'avete messo orizzontale? Che è successo? Va bene. Va bene.
Okay, so that's okay, perfect. So let's start. Now, talk to us about innovations in public meetings, creation and mathematical properties.
Yes. Thank you to the organizers for the
Which one?
It's all.
okay. Thank you to the organizers for this opportunity here in Catania. I try to avoid slides as much as possible, so that's why I'm trying to do the talk with let's say old-fashioned. Okay. Okay.
Okay, sorry. Because okay, it's close. That's the fish. Che è successo?
E l'audio questo audio?
No.
Ah, okay.
Era questo qui era acceso. Era questo qui, c'erano due microfoni accesi.
Ok.
Forse anche quello girato. No, basta. Oh, don't speak.
Okay. Can you do it? Yeah, thanks.
Era la gomma. This is the rubber.
No, okay.
That is the rubber.
Okay. So, also, I'm sorry because I'm not an elliptic guy. I'm going to talk about an hyperbolic problem.
Okay.
Nobody's perfect. So, let me start. So this is for funding purposes. I have to mention that this is about cold plasmas, and I have no idea what a cold plasma is actually. Strictly speaking, I don't know what a plasma is, so it's something weird for me. But the PDEs that model the dynamics are rather interesting. So we have a. Why is this thing recognizing letters?
Che non so.
Che disastre.
Like this. Like this.
You like this?
Yes.
Okay.
Okay. Okay.
You're welcome.
So So here we have an electron cloud, and the density is n. Okay, and then there is u. This wants to be a u. Let me try to do it better. So, like this. In this tablet, I write like a 6 years old kid. Sorry?
Yeah, very close.
They will change in a minute.
Okay.
So, and then we have the velocity. And there is the magnetic field. And so we have a system of hyperbolic, elliptic equation. And then the probability of having every sign correct are almost zero. Yes, so like this. Okay. So this is not a model, but the full system under a number of assumptions, like one directional motion, ions, and electron having the same density at time zero, and so that thing will propagate, and a number of other things like that. Okay, so but this is just the full equation. And this system has been studied by many authors, like since the 60s. So the Granero and Morikawa in the 60s. And since then, Catania, Ono, and many other people. Okay, so so this is the system I'm going to consider. Okay, and for this system, what we managed to prove, and this is a joint work, we just put it on the archive like 2 days ago or something like that. With Diego. Alonso. And Angel Duero. Okay. So for this system, we first derive the asymptotic model. And the models are non-local, hyperbolic equation. Okay, so the advantage of the asymptotic model is that you can reduce the original hyperbolic elliptic system to either a couple of hyperbolic equation of Boussinesq type, paired with a non-local nonlinearity, or a single weight equation, which of course has the a non-local nonlinearity too. Okay, and so these three asymptotic models are simpler than the original system, but at the same time capture the main dynamics of the original problem. Okay, so this research topic on asymptotic models and its behavior is a classical topic since the 19th century, for instance, when for waterways, right? So we are just trying to adapt this program for waterway to this problem in cold plasmas. Okay, and besides this new equation that we found, we also managed to prove well-boldness, local well-boldness in subgroup spaces. Okay. So, and this is the thing I'm going to focus on. So let me, instead of, so this is just, let's say the summary. And I told you that there are three asymptotic models, but we forget about it. I'm going to focus on just one, okay? And the equation that I'm going to consider, and now U and N disappear, is this one. Now I will display what this thing is in a minute. Okay, so here, so this is, so I said that this guy is a wave equation just because of the two derivative of in time, but L is not the Laplacian. L is the operator with multiplier with this multiplier, okay? And N has this. Okay. So the derivative of N is minus L, okay? And the double bracket is the commutator. So I want to convince you that that the problem is well posed. I mean, with the classical notion of solution, okay, is locally well posed, and it's not that question is not completely trivial because if you see the right hand side, the nonlinear term has a way too many derivatives compared to the linear part, right? So L is basically a perturbation of the identity. So in a sense, the linear part of this guy is basically the harmonic oscillator plus a regularizing term, if you want to think on that way. Okay. So so in order that equation can be locally imposed in classical terms, we have to exploit the structure of the nonlinearity. Okay. So we have to find a cancellation that allow us to close the estimate. Okay, so this is the problem. So let me state the theorem I want to show you. It's kind of weird to give a talk here being seated. So, it's very weird. I usually, when I give a talk, I usually use the blackboard, and I was walking and yelling to other people like,
No.
this is the important term, and this is the bad guy, whatever.
Yeah, in Italy, we don't scream.
No,
We just stay quiet.
Okay.
We just don't do like this. No.
Okay.
No, just.
Then
We do not know such things.
Okay. Then for me, it's very weird to be here just talking. Okay, so give me an initial data that is in. Okay. This guy is in H4, and this guy is in H3. Okay, H1 is the initial data for the velocity, for the H1. Okay. And assume that this guy is less than 1. Okay, and there is a reason this one is that one. So if you allow me to change that one by 10, I can have both guys will be 10. So in a sense, this is not as a small data result. Okay. So you can so if the homogeneous state is large, the perturbation can be large. Okay. Then there is a local solution. By smooth, I mean with the same regularity. Okay. So let me try to convince you that this is true. And as I told you, it's not obvious because this guy is losing derivatives somehow. Okay. So let me introduce the following energy, and I'm going to try to show you how to do the energy estimate. Okay. Then the local solution will follow from the energy estimate with a regularization approach that you can use whatever you like modifiers or whatever. Okay. So this guy is going to be also, let me introduce something before the energy. Everything is written in terms of H0 minus 1, so let me use that. And now, okay? So it's the perturbation from the homogeneous state. And if we write the equation for this variable, this guy doesn't see the 1, but the nonlinear term does see the 1. Okay. So now you can see why I want the homogeneous state, and this is the homogeneous state is interesting because this one with this guy and this guy will give a wave equation. Okay. But even with that wave term that we found from the homogeneous state is we are still losing derivatives. Okay. So now we define the energy. L is a positive multiplier. I mean, L is the operator given with a positive multiplier. I can take the square root of that guy. And then this guy. Okay. So as I said, these two. Let me try to. So this guy will come from this guy. Triangle will come from triangle, and then the square will come from square. And those are the linear contribution. Okay, and then we have to estimate the nonlinear terms. Okay, and then we test against this guy. Probably no, actually with minus that guy. If we test the equation against that term, then the linear part give us the desired energy. Okay. So with the maxes I told you about, we will have time derivative of the energy less or equal than the nonlinear terms. Okay. And then there are a bunch of nonlinear terms, but let me focus in
that guy.
So, believe me that the other terms are like this. The commutator and all that. The commutator is not local, but it's gaining derivatives. L is a perturbation of the identity, and so the commutator will disappear for the identity, and the perturbation is a regularizing, is a Helmholtz operator basically. So remember that L is that multiplier. So basically, L is the identity minus 1 over 1 plus chi squared, and so that thing gains 2 derivatives. So the commutator either disappears or gains 2 derivatives. And so the main problem are from this guy. So after testing against that term, so we have a nonlinear plus a guy that is omega xx dx6 omega t. Okay, plus minus, I don't know. I always fail with the signs. The problem is whether you have an odd number of errors. Probably I have an odd number of errors here, but the thing is, so believe me that this is the bad guy. Okay? Or minus this guy is the bad guy. And this is the integral over the whole real line. And so here I control 3 derivatives of omega t and 4 derivatives of omega. And there are way too much derivatives, right? So if I split, let's say that we support social justice. We want to remove some derivative from this guy with 6 derivatives. This guy has way too much derivative. We want to share it, okay? And if we do that, so so this is the bad guy. Let me move derivatives. Then we have omega 1, 2, 3, 4, omega t 1, 2, 3, and 4. Okay. So this is the bad guy. I'm losing 1 derivative in the omega t. Okay. So how can I fix that? I cannot just remove one. I cannot integrate by parts once, right? Because if I do that, then I lose 1 derivative in omega, right? Because remember, I control either 3 for omega t or 4 for omega. So either I lose 1 derivative in omega t, because I can only control 3 and I have 4, or I integrate by parts once and then omega t is okay, but then I lose 1 derivative in omega because I can control 4 and I will have 5. Okay? So the trick here is that I have to integrate by parts, but in time. So I have to integrate in time and then integrate by parts in time. And if I do that, that term will become 0t. Also, I have to use Houdini and all that. And then I can move the time derivative, right? Because this is a perfect time derivative. I can move the time derivative and I get this. Again, I minus whatever. So one has to check the signs, right? But this is not an energy term, so we will bound it. So it doesn't matter whether I'm doing an odd number of mistakes. And now I'm not losing derivatives because I have 4 for omega and known for omega t. Okay? So it seems that we won, but this is a problem because I cannot use Grunwald anymore. If I integrate in time, I cannot use Grunwald, right? I already did it somehow, right? So at the end, I have to define a new energy. Sorry. Which is the supremum of my old energy. then I have this polynomial inequality. I have 3 halves, but I can simplify my life and say, okay. And now let me try to explain why this thing makes our life much more comfortable. That polynomial looks like this. Terrible picture. Okay, drawing is not my main skill. So basically, that polynomial looks like this. And my solution has to live in the positive region. Okay, so either my solution lives here or my solution lives here. Okay, and because of how this polynomial is, actually on my solution at time 0 is right there, and that's how we have a uniform bound, because you cannot leave that small region. And so, for instance, if this is 10, the energy is less than 10 because it cannot cross to the other red region. And with these two ideas of the integration in time and the polynomial inequality, we managed to prove the local existence. And that's basically what I wanted to tell you. Okay, so from the starting problem, so basically you consider a perturbation n, you consider n a perturbation of 1, so and you use an asymptotic expansion of the type n equal 1 plus epsilon h plus epsilon squared h2 epsilon cube h3 whatever, and then this nonlinear problem can be written as a cascade of infinitely many linear problems. Okay. Basically, this is an idea that goes back to Boussinesq or Rosine at the late 19th century or the beginning of 20th century. So basically, every nonlinear problem of this type can be written as infinitely many linear problems. And then we solve it. And we solve it, and then we can just plug the solution that we have. We solve the elliptic problem. So the solution will be explicit in terms of the Helmholtz operator, and that's how L appears. Okay, so we are just basically after after introducing the answer, we can solve the elliptic problem explicitly. We will have this L operator that came into play, so we just plug it. We truncate the series up to the Desai order, in this case squared. That's why we get a quadratic nonlinearity. If we want to keep adding terms, we will have a cubic equation and all that. Okay, and that's how you get the asymptotic model.